So the last thing I want to talk about is what we call the inaccessible point. What this means is this point up here, point P, I don't know the elevation of it. So there's a couple ways to figure it out. One is you can get up on top of that stack. You can get up there and somebody can have an instrument on the bottom and you can hold the rod up on top and you can get an elevation up there. That's one way to do it. A little unsafe and probably wouldn't gain access to it either. So there's other ways to be able to do this by using coordinate geometry, by using these common equations that we just talked about. So if you look at the elevation of P, the way to figure that out is if you had a known elevation right here, elevation of A, right, isn't just the height of the instrument we have. So if you set up an instrument right here, set up the instrument, this line right here is shown to be in the horizontal plane. So if I know point A, all I need is the height of the instrument at point A, plus then from that horizontal plane right there, the elevation then of from I to P, that distance from I to P, which would give me then the elevation of point P looking at it from point A. So up here the elevation of A plus the height of instrument plus the length of IP from A. So now we need to think about this, the IP to A. Before we get to there, understand this. We have two control points. We have A and we have B. This is all we have, and then we have a distance right here of A to B. And the only thing we're measuring then is we measure a distance from A to B. We measure this interior angle, and we measure this interior angle. We never do come over here there to do it. And we measure this vertical angle and this vertical angle. That's all that we're measuring as we do this and be able to solve for this. Never once are we up near the building or up near the stack right there to figure out any sort of elevations or anything else. Okay, so keeping that in mind, we want to know then the distance of IP from A, of course. So what that does is it tells us, all right, what's the actual definition and how to be able to solve for that. So if you look down here, put down here IP of A is equal to AI. So we need to know this distance here. We need to know AI times the tangent of the vertical angle. So the vertical angle we measured. Like I say, AI we didn't measure yet, but we're not through yet. We can be able to, I think we can figure out what that is. So let's put that back in our equation now. So all I did was take IP of A and then plug in what we just solved for down here up to there. Now this is what I'm talking about to be able to compute and figure out what AI is. Okay, that's our other unknown, what we didn't figure out anything. And I told you before, we measured the distance from A to B. We have that distance. We have interior angles here at A and at B. So based on that, what that tells me is we have one side and two angles. So through the law of sines, we can then solve for another side, which in this case we're looking for AI. In that case right there, here's your equation. And you can go through and figure out how I came up with that. Just simple use of law of sines, that's it. So now that I know what AI is, let's go back and plug it into the equation. Now the last thing we don't know, however, is I. I is pretty simple though to be able to figure out. I'm sure you see what we're talking about there. I then is simply, if this is a triangle in the horizontal plane, it's 180 degrees minus the sum of the angles of A plus B. And there then is your final equation right there. Something that seems simple for you to just walk up on top and make a straight up measurement, we end up with something like this. All the way back from what I wrote to say, all right, this is what it is. Three components, elevation of A plus height of instrument plus the distance of IP. It's the distance of IP that we can't do anything about until you make all these other additional measurements, the angles at A and B as well as the vertical angles and the distance from A to B. Based upon that information, you can then solve for the elevation of point P. Now we can do the same thing solve for P from point B. You always want to check yourself, so it's not just good enough to do it once. You want to do it from both sides to make sure what you're calculating is correct. So now let's go through that same process. We need IP from B. You can see the different distance because now the height of your instrument right here puts you on a different horizontal plane. So this BI, that's what that's representative of, going up to this point right there. Alright, so we go through and do the same thing we did before. We need to solve for IP from this side, which is the length BI times the tangent of V2. Now we need to solve for BI. Again, it's from that same equation, the same triangle we used in the horizontal plane to solve for BI by the use of law of sines again. So plug that back in. Last thing we solve for again is I, which we know is 180 minus the sum of A plus B. And then here again is your final equation. So great, now we solve for point P from two locations. So in the end, what we end up is this. We solve from point P from A, we solve from P from point B, and we're just taking the average. So this is your final equation. To solve for this, you can take an average of the 2 points, and that way it's a check to yourself to make sure what you did was right, what angles you measured were right, the distance you measured was right. I wouldn't even say right, but it's that it correlates with one another, that it checks with itself, that you're not making one single equation. It almost relates to when we talked about radial surveying, making one measurement to a point, single measurements, that's it, you have nothing to check yourself. By doing this and calculating, computing it from both locations helps you to make sure that you didn't have some sort of error inside your calculations. So that's the two big ones I want to make sure you understand, is a coordinate transformation, as well as, here's just a good example of just looking at any problem and you figuring out what is it I need to do without having to injure yourself, risk your life, or do anything different. You look at the problem and solve it from where you're at. Instead of trying to figure out extreme ways to be able to go about it, there's a lot of other ways that you get to approach this to be able to solve for the information that you're looking for. And that's the benefit of using what we call COGO, coordinate geometry, using these equations that you use the known locations and angles to figure out all this information indirectly from the direct observations that we can get.